Okay, so thank you, Tom. Our next speaker is Greg Retallack of the University of Oregon. Greg is an award-winning paleobotanist whose research group is dedicated to soils in the fossil record. His studies have considered the role of soils in ape and human evolution in Kenya, grassland evolution in North America, and several others. He recently published a paper titled Global Cooling by Grassland Soils of the Geologic Past and Near Future in the Annual Review of Earth and Planetary Sciences. Please welcome Professor Greg Retallack.
Thank you, Seth and Tom. A lot of what I would say is actually going to be preaching to the choir, I'm afraid, but what I'm going to try to persuade you is that grasslands actually did cool the planet once, and they could do it again because they cover such a large area of the planet. However, it wasn't always so. There was a time when there was no grassland at all. And this time when there was no grassland at all was sort of very forcibly impressed upon me when I did fieldwork in Antarctica for many years. I worked on the great life crisis of the Permian Triassic in the wastes of Antarctica. And this was fieldwork out of a remote camp in Victoria Land, out of McMurdo Base. McMurdo Base, as many of you know, is the US main base in Antarctic research, and is sort of making a transition from a derelict military camp to a love boat, a university campus. So when we came back from the field, some people in the mess invited us to a margarita party in the dorm. There are dorms at McMurdo. Who knew? So we turned up to this sort of dorm room. A couple of girls were sponsoring this party. And when everyone was there who was going to be there, they said, well, how about some grass? And I thought, well, really? I mean, this is the US Antarctic program. There was sniffer dogs. There's no drugs in McMurdo. We didn't have a whiff of them. Sure enough, she went to the window behind the thick curtains, which were meant to give the impression that this was a nighttime party after all, for adults. And she brought back this lovely ceramic pot of Kentucky bluegrass, which she had been growing in her windowsill for the last, almost a month or so that she'd been at McMurdo Base. I was absolutely stunned because we'd been out in the field, and McMurdo itself is actually a pretty sterile environment too. Just the smell of this grass just was absolutely overpowering. It was so wonderful. I'd had this experience before in climbing in the New Zealand mountains, coming off ice caps after several weeks down into the alpine grass. So we handed this pot around between us, and we said, man, this grass is so good. So that's my first message to you. Smell the grass, folks, because it really is wonderful. We know the compound that does it. It's actually the same compound that makes watermelon and green tomatoes smell so good. This is the key. This soil here, it's a mollisol or a grassland soil, a very characteristic kind of a soil created by and for grasslands. I'm not so much of a soil scientist as a fossil guy, and I've been very interested in looking at what we call paleosols. Paleosols is the study of paleopodology, which has nothing to do with Egyptian mummies' feet or Sumerian school children's psychology. It's actually the study of ancient soils. And this is what they look like a lot of nothing to most geologists. These rather subtle bands here are actually a sequence of fossil soils. I've labeled them here and shown where individual soils are, and I like them so much and think they have so much character, I've given them names in the Sahaptian Indian language, Nix and Talal. You can see here there's a whole sequence of paleosols here, which I believe is an archive of change over the last 100,000 years or so. These are records of ancient environments that tell us how the Earth has changed in deep time, independent of the usual records that we have, the pollen and spores, the phytoliths, the mammal bones. They're in these rocks as well, but we have this independent record of what the Earth was like in the past from sequences of paleosols. We can get isotopic and other lab data, which I show you there, but let me just go on and talk about how you recognize these two different sorts of ecosystems in the field. You can do it in the field, which is really quite wonderful. This is a sequence of paleosols here in this road cut, and we have dates independently from Alan Busaka and his colleagues. There are two kinds of soils, remember, Nix and Tallal. The Nix has this wonderful crumb structure to it, these tiny little roots. These are crumb peds, and they are characteristic of mollisols, or grassland soils, the tiny roots, the crumb peds created by earthworms, and also by the fact that the roots are very finely branching. This is characteristic of a fossil mollisol. It's no longer very dark or humic because nature is pretty conservative about carbon. If it gets buried above the water table, it will be eaten up by microbes and move elsewhere. The other paleosol type, the Tallal, has these interesting burrows in it. This is a burrow here, and it has these cross partitions where the insect moved through the material. We know what this insect was. It's an insect called Okanagia. It is a cicada or cicada, and it is an obligate sagebrush insect. And so from the sequence of paleosols, we can see over the glacial, interglacial conditions that there was interglacial grassland in this area and glacial rangeland. So this part of the Palouse Prairie of Washington alternated from its current state of being a grassland, currently under pretty active agricultural exploitation, I might say, during the interglacial periods, and it was a sagebrush steppe during the glacial periods. Now that's not very deep in time. Let's go back into deep, deep time here in Central Oregon. Some of my favorite outcrops in the John Day Fossil Beds National Monument. You can see them in the background here, these green beds. We're talking about quite ancient deposits which have an absolutely splendid fossil record of mammals, which we can use to date them. We can also get the dates from these radiometric ages. These are the fossils that we use to tell the age of the rocks. We actually have ages in millions of years from an argon technique of dating the rocks, and we can make an age model. This is a tremendous pile of paleosols. You might not have realized that there are about 1,000 paleosols through here, through almost a half a mile of sediment. And this is a long-term record of climate and vegetation through time. Now, I've given you a little bit of basic information about how to tell a grassland soil from a sagebrush type soil. We see this back in deep time as well. Here are the cicada burrows from an Oligocene age paleosol. We're now talking about 30 million years ago. Here are dung beetle balls from a grassland paleosol. Here are earthworm chimneys from a grassland paleosol. This is the Ctenidium, which is the sagebrush ecosystem. They're only in the paleosols that have a very shallow BK horizon. The BK horizon is a horizon of calcareous nodules that are found in arid land soils. If the BK horizon is a little bit deeper, then we get another assemblage of dung beetle balls here, and Oedophycnium, which is the name that we give to the earthworm chimneys. We give these things names because we're not quite sure what formed them, and we want to be scientific about it. It's what we call ichnology. It's a different discipline of paleontology. But look at this. You can see very clearly, way back in time, 30 million years now, there's a clear separation between the sagebrush ecosystem, which is the one that's not that agriculturally useful, and the grassland ecosystem, which is the one that is exploitable. These records are quite comprehensive. Let me now go beyond just the sagebrush grassland and show you a few more things. The characteristic soil profile that's formed by a forest is one we call an alpha sol, and it's way different from either of the paleosols that I've talked about so far. It has a BT horizon, which is rich in clay. Here's a glade upper horizon with big root traces going down. The big root channels enable the channeling down of clay to create a very clay subsoil, like you have through quite a bit of New England. The grassland paleosol, on the other hand, has these lovely crumb peds. Here's a tall prairie grassland, dated about 7 million years old. Here's a shortgrass prairie paleosol because the BK horizon is fairly shallow. Here's the BK horizon only about 30 centimeters below the surface. Here's the BK horizon of calcareous nodules here, in this case about 80 centimeters below the surface. So we can tell a shortgrass prairie from a tallgrass prairie from a forest, and a few other sorts of soils as well, and come up with narratives of what the origin of grasslands were in 3 different parts of North America. Oregon on the bottom, Montana in the middle, Nebraska in the top. Now, this is a very detailed graph, but my main point about this is that many people, when I started this work, thought, oh, obviously grasslands evolved to fill in the dry spots as the continent dried out with the rise of the Rocky Mountains creating a rain shadow. Sounds perfectly logical, right? That's the null hypothesis that I had to deal with. What I found was that there were shrubland paleosols, or sagebrush-like paleosols here, that went all the way back through the record. Those ones with the oak and not in Oregon, but particularly in Montana, and a fair way back in Nebraska. When it got dry, it didn't go to grassland, it went to arid shrubland. The grasslands, on the other hand, appeared at times when there was a bit of forest around. The bunch grasslands at first appeared back here, and back here, and although they fluctuated in their abundance through the landscape, they didn't go away. They were always a part of North America. The sod grasslands appeared quite a bit later in the Middle Miocene, around about here and here and here, which was again a period of warm, wet conditions. The grasslands appear, in other words, to be a biological invention. Many of us have raised on the idea that plants and animals adapt to their environment. But plants and animals also are capable of biological invention. And once you get a good idea, like computers, for example, or smart cars, there's no stopping it. It may fluctuate in its abundance through time, but it keeps on going. And this made me start thinking there's something kind of odd about this and its relationship to climate. We can also get climate from the paleosols themselves, and I won't go into how we do that exactly. We can get it from two separate proxies, from chemical proxies, and also from depth to decay, which is in the red here, and they match each other quite well. But there's something really odd about this. There are these sharp spikes. That's really odd. We think we understand what those are. The really difficult thing is, why for 10 million years did it hunt down to this low level? This is mean annual precipitation now, and I could show you similar graphs for temperature as well. It's the long-term declines in temperature and precipitation that are the mystery, not the short, sharp spikes. The short, sharp spikes, we know about those. Those are disasters. Those are a variety of disasters, including meteorite impacts and including large-scale volcanic eruptions of unprecedented volume. Back at 35 million years ago, remember that's when the bunch grasses appeared, we have a big impact in Chesapeake Bay, and we have these huge Ethiopian traps. In the Middle Miocene, which is another set of these spikes, we have huge eruptions of the Columbia River basalts in Oregon and Washington and Idaho, and we have meteorite craters in Germany. When you get a big injection of carbon dioxide, either from volcanic eruption or from vaporization of ecosystems into the atmosphere, you get a spike. But what causes the drawdown? That's the question, isn't it? Now, some people propose that the drawdown was created by the uplift of the Himalayas. The idea is that mountain uplift would promote weathering, and that would draw down carbon dioxide, and that it would also give a greater albedo, which would shift sunlight energy and heat back out into space. Both are quite mistaken. The uplift of the Himalayan does not promote chemical weathering, it promotes physical weathering. Chemical weathering is what you need to pull down CO2. Physical weathering just moves stuff around like a bulldozer. It doesn't actually interface with the CO2 at all. Furthermore, when you took the Tibetan Plateau up from the former forest that exists in that area, there should be actually a decrease in carbon sequestration altogether. And that uplift also was associated with deep metamorphism, which in itself will degrade limestones that are very deep in the earth and release carbon dioxide through many carbon dioxide springs that are all through the Himalayas. I think this explanation is just wrong on its face, and I can make arguments from timing as well, but I won't go there in the interests of time. The other textbook explanation we often find for this long-term cooling from the heat of the late Eocene and then the spikes of the Middle Miocene is that it has to do with the thermal isolation of Antarctica. Back at the beginning of the story, in the early Tertiary, Antarctica was attached to South America and Australia, and the currents, the global heat engine, actually bathed the shores of Antarctica so that Antarctica had hardly any ice. As it drifted away, progressively, we started to find the beginning of the circumantarctic current, which isolated it thermally, and so it grew ice. But the question is, would this actually create a global cooling of the whole Earth? Well, computer models have now confirmed what common sense would dictate. If you cool one part of the planet, other parts are actually going to warm up. This would actually warm the mid-latitudes if you're cooling the high latitudes. The albedo effect would be actually quite minor in that high latitude because the sun is not really reaching it for half the year anyway, and it's at a very high angle. So I don't think this explanation, which we see in a lot of textbooks, is a very useful one either. My explanation has to do more with biology. This is several different parts of the world, and I'm glad to say I could add Argentina to this now from my fieldwork just this past summer. The amazing thing about the sod grassland ecosystem, let's just concentrate on that now, this green, is it started, there was none before about 20 million years or so, and then it seems to have expanded its range. How could that have been? How could it have expanded its range into wetter climates? Remember, this axis on the bottom is mean annual precipitation. Grasslands were on the march, folks. They were taking over. They were hardly any to begin with, and then they expanded on their own, independent of climate. The answer, I think, is coevolution. The answer is that there were a series of biological inventions that were the product of the evolutionary interaction of grazers and grasses. Coevolution is a wonderful thing, and you've all seen this in textbooks, I'm sure. The evolution of horses into high-crowned teeth suitable for grazing, the evolution of doggy-style limbs through to horse-style limbs with hooves that were hard on the sod, the evolution of a whole variety of features in grasses, including dense investment with phytoliths to deter grazers. What's happening in coevolution is not the usual idea that organisms are adapting to their environment. They're adapting to other organisms. Environment be damned. It reminds me of fraternity and sorority parties. They're not interested in keeping their house neat. They're interested in the opposite sex and having a good time. And of course, the whole house gets trashed. In this case, however, the coevolution of grasses and grazers, with the grasses the only things that could withstand the onslaught of the mammals, did something rather wonderful. It created a whole new kind of soil, the mollisol, with this deep, crumb, humic texture to it, which was an unprecedented carbon sink in the world. And this gradual adaptation of grasses to grazers and grazers to grasses, I think, is the explanation for the drawdown of CO2 and declining temperatures from the peaks of the distant geological past, 35 and 16 million years ago, into the Pleistocene Ice Age. There's one more piece of it that I think is really interesting. At about 17 million years or so, we suddenly got sod grasslands. Why was that? Well, I think the grassland ecosystem as we know it now was actually the dream of a dog. We have this wonderful evidence in the brains of fossil dogs, shown here, that around about the same time we see the development of the prurient gyrus, this area of the brain here, which is known to be an area found only in pack hunting dogs as opposed to solitary hunting dogs. So what happens when suddenly dogs make the biological invention for the first time ever of pack hunting? Well, all of a sudden we get a cascade of effects. We get the first herds, which actually date to this particular time. We get the first mollisols. We get the full onslaught of fairly high-crowned teeth and these rather elegant leggy look that's so much in demand these days. We get the first dung cakes. We get the first mollic ecosystem, which is for the first time in the world. And this, I think, was the beginning of the drawdown that we see going on into the Pleistocene. So let's get to the nitty-gritty. How did it do it exactly? Well, three ways. There are more, but I'll just go through three. First off, this grassland ecosystem stores more carbon than other ecosystems. Australia, my home country, has virtually no carbon in the soil, and it shows this relationship with mean annual precipitation. This is actually largely European agricultural activity, and this point through here. In Africa, look at this. Look how much more carbon there is in this range here, which is the critical range for grasslands. That mollic epipedon sucked CO2 out of the atmosphere on a geological timescale. Grassland soils also are very interesting in their transpiration. Many of us had the experience of sweating through a tropical forest and then digging down into the soil and finding the soil almost dry. On the other hand, if you walk across a Kansas prairie in the summer, you're sweating because you're absolutely hot and you're getting dehydrated, but if you dig down in the soil, that soil is moist. Grasses and the sod are very protective of moisture in the soil, whereas the trees just transpire every little bit of moisture they can get, and they transpire particularly between the trees and then up into space, create their own weather patterns. Water itself, water vapor, is another greenhouse gas. It gets rained out, so it's not like CO2, it doesn't hang around forever, but it's another greenhouse gas which contributes to the warming of the atmosphere, whereas the spread of grasslands would have been a cooling effect. And then finally there's albedo. Even if there's not snow, grasses are lighter colored than trees, almost all trees. And grasses, of course, often wither back in a dry season or a cold season, so they become yellowed and they reflect more sunlight out into space. And of course, when the snow falls, that effect is exacerbated considerably because it's all bright and the vegetation is actually beaten down by the snow. Now, I don't need to go too much into carbon farming, but it seems to me that there are many parallels with what I'm saying here in the geological past with carbon farming technique, and I particularly like the idea of cell grazing as a recreation of the original kind of shepherded agriculture and the original pack hunting that made the ungulates cluster into herds. And finally, let me sing my conclusions. There's some good news beneath the horizon. Next to swamps, grassland soils have more carbon. Since these are the soils that we already use, we can manage soil carbon and curb soil abuse. It was just coevolution, a process by which we got sod. By grazing so hard on grassy sward, the ice age no longer seems odd. Still we have coevolution, a way that we can go forth and use the soil against Big Isle to try to cool the earth. Thank you.